Hello class, so this is 2.4 atomic weights. Hopefully it's going to be a quick video, pretty quick notes here, so let's go ahead and get started. With your atomic weights, there's an atomic mass scale. So this is kind of background information as to where all of our atomic masses came from. This is not really important information, but it helps give some background knowledge for AMUs. You don't have to write this down. It also is kind of written in the beginning chapter of chapter 2 for section 2.4. So if you want to follow along in your book, this is kind of where I'm getting this from. Again, not super important, but gives some context. So back in the 19th century, their thought process, if they took a 100-gram sample of water, they were able to separate the hydrogen from the oxygen, and they found that 11.1 grams of hydrogen was in 100 grams of water, and 88.9 grams of oxygen was in this 100 grams of water. Then they compared the masses of oxygen and hydrogen. So they said that 88.9 for your oxygen for every 1 gram of hydrogen, 11.1. So you've got 10 times as much oxygen as you do to hydrogen. So they took oxygen over hydrogen. You've got 8 times as many oxygens as you do to 1 hydrogen. Now, they later discovered that water was H2O. So that means 2 hydrogens and 1 oxygen. Therefore, for the mass of 1 hydrogen, you had, here's the 8 times from earlier, and then the 2 having it being H2O. So 2 times 8 is 16 times as much mass from the oxygen as the hydrogen. Okay, 16 times as much. The hydrogen atom is the lightest, so they arbitrarily assigned it, say that 10 times fast, arbitrarily assigned it a relative mass of 1. That's without any units, and then they compared everything to this relative mass of hydrogen to be a 1. So, for example, hydrogen equaled 1, oxygen equaled 16, carbon might have equaled 12. Kind of continued on this theory, so that was 19th century. Today, thought we have a little bit more information that we can be more exact. So we know that a H1, so again, that's your mass number, has a mass of 1.6735 times 10 to the negative 4th grams, and your oxygen 16 isotope has 2.6560 times 10 to the negative 23rd grams. However, those are in grams, and grams are really, or these numbers are really small, really small masses. So they use an AMU unit, the atomic mass unit talked about in section 2.3, in order to make these measurements more convenient. Some conversion factors for AMUs. 1 AMU is equal to 1.66054 times 10 to the negative 24th grams. That is the definition of what an AMU is. And then here we've got 1 grams containing Avogadro's number of AMUs. So those are conversion factors that you use. A little trivia fact for you. The periodic table nowadays, instead of being based off of hydrogen or off of oxygen, it's actually based off of carbon-12 and exactly 12 atomic mass units of the carbon-12 isotope. So, average atomic weight. Okay, this is the important part. This is what you need to be able to do on the AP Chem test. If you look on the periodic table, then you'll notice that there are decimals there. Yay! So, why? Why are they decimals? Because we know that the mass number is protons and neutrons added together. Well, if you're looking at carbon, hopefully you don't have 12.1 of a proton. We need whole numbers of protons and neutrons. So the reason why there's decimals is because we're looking at all of the different isotopes of carbon or all of the different isotopes of the elements and looking at their average atomic weight. Most elements in nature are a mixture of isotopes, which is why we have to look at all of the isotopes to look at the atomic weight. Okay, big ugly equation. Your average atomic mass, that's what I call it most often. Your book calls it average atomic weight. Mass and weight are kind of the same thing except for gravity. So average atomic mass, average atomic weight, assume they're the same thing. This little happy E or sideways M symbol means sigma. You're basically going to, it means the sum. So you're going to add everything together. And then we've got the isotope mass times the fractional isotope abundance. And then that's for all of the isotopes of the element. This will make more sense. Bear with me. Let's just go ahead and do the example to have more sense. So your example, we've got naturally occurring carbon, for example, is composed of 98.93% carbon-12 and 1.07% carbon-13. The masses of these isotopes are 12 AMUs exactly. Remember that an exact number is a definition, or it's actually been counted out. It's not measured, actually counted out. So we don't have sig figs for that 12 AMUs. 12 AMU exactly and 13.00335 AMUs respectively. Calculate the average atomic mass of carbon. Okay, I'm going to put that equation back so that we can look at it. And this is for each of the isotopes. So first, we're going to take one of the isotopes. Let's take carbon-12. We need the isotope mass. Okay, our isotope mass of carbon-12 is 12 AMUs. So we're going to put that here. And then let me grab my pen. Now, this is fractional isotope abundance. It says fractional, not percentage. So in order to get this into a fraction, we're going to move our decimal 2 places to the left, and we get 0.9893 hundredths. That's how we're going to write our abundance. So here's carbon-12 isotope mass. Here's carbon-12 isotope abundance. That is our first isotope. So that's this whole thing for our first isotope. Then again, the sigma means sum. So we're going to add the isotope mass for carbon-13 and the fractional isotope abundance for carbon-13. So we're going to do that for the second isotope. So there is our mass of carbon-13 isotope times our abundance of the carbon-13 isotope. Again, we moved this decimal 2 places out so that it's no longer in percent, it's instead as a fraction. That's kind of our breakdown of our equation. Here we go, plugging it into our calculator. So if I'm doing just this part first, plugging it in, we get 11.8716 AMUs. If I'm doing the second part, multiplying it together, we're going to add that to 0.13914 AMUs. And if I'm looking at all of those added together, I get 12.0107 AMUs. Now, big long sig fig discussion we could go into. My main goal is if you can round this to 2 places after the decimal, we'll be okay. So that rounded to 2 places after the decimal would be 12.01. Don't worry about sig figs. We might touch on it in class for this, but it's really not that important. Cool. So there's the equation, and then there's an example. So for this next one, I would like you to solve this on your own. Go ahead and calculate this using that same equation. Rubidium has 2 naturally occurring isotopes, rubidium-85, which has the atomic mass of this, and our abundance of this, 72%. We've also got a second isotope of rubidium, which is rubidium-87. So we've got atomic mass of this value in AMUs and the abundance of this value. So calculate the atomic weight of rubidium. Hope you did that. If you didn't, here's kind of a double check. 84, so we've got our atomic mass here. That was from our example. Again, we've got that percentage that we moved our decimal for. That's for one of the isotopes, isotope rubidium-85. Then we've got our second isotope, so this is the mass of the second isotope and its percent abundance of the second isotope. Again, move our decimal. Multiply those together, add them, you should get this value. Round it to 2 decimal places after the 2 places after the decimal, and you get 85.47. Sweet. Second part of these notes is 2.4 mass spectroscopy. This is in your book. It's called A Closer Look, but AP Chemistry will ask you questions about this. So if you want to go back and read it in your book, not a lot of information, so let's talk about it. First, a mass spectrometer, that's basically your computer, so it's an instrument that provides the most accurate means for determining atomic weights. This is what we use to be so specific that it actually measures like all of the protons and neutrons. Here's how it works. So ultimately, you put your sample here in A. We've got a heated filament and an ionizing electron beam. Ultimately, this process turns your sample into a positive ion. So it will pull off the electrons and make these all positive ions. And you do this for different isotopes, so it separates your different isotopes. Then it's kind of got this accelerating, well, again, it's a vacuum, so this is empty air. It's got this accelerator, so it's going to speed up and like shoot those ions through this accelerator, go straight through this little slit, so you've got a beam of them. Then we're going to put a magnet. Now again, these are positive ions, so depending on the weight, they're going to move around that curve. We've got this kind of curved glass in a magnet. They're going to move around that curve at different speeds because, for example, chlorine positive 37 and chlorine 35 positive, they're different masses. They're different weights. It's kind of like taking a really big bowling ball and moving it around a curve versus a ping pong ball around a curve. The bowling ball is not going to curve as much. So then we can separate our different ions based on their masses. The magnet is here to also separate the ions based on charges. So if we were looking at like a positive 2 charge ion versus a positive 1 charge ion, that will help with the magnet. So we're looking at mass as well as our charge. Hey, we've got a mass-charge ratio. There we go, bringing that in from Millikan and Thompson. We'll get examples of this, but ultimately it separates these two ions. Then we've got another slit that just isolates this one ion. It comes through to our detector. And then our detector is connected to a computer that actually analyzes the percent abundance of this. Then they can change the strength of the magnet and the curve of the tube in order to isolate the 37 chlorine ion. So, what is it all used for? The information that the computer spits out is called a mass spectrum. Spectrum is singular, I think, and then spectra is plural. So the mass spectrum is the graph of intensity versus atomic mass. Anytime you see something written like this, intensity versus atomic mass, the first one is on the y-axis and the second one is on the x-axis. So this is doing a graph where our intensity is on the y and then our versus atomic mass is on the x. So for this particular example, it might look something like this. We've got intensity, meaning how much of our sample was chlorine 35 and how much of our sample was chlorine 37. So based off this graph, we can say that our intensity was pretty high for chlorine 35 and kind of low for chlorine 37. Also, if we look at the relative height of this one's about 3 times as much as this one. Our spectrum will provide masses for the particles and the relative abundance, so that's everything we need in order to calculate average atomic mass, masses and their abundance. And then we can use this in order to identify chemical compounds or mixtures. So if we put some unknown sample in it and it spits out these ions, then we know that we've got a sample of chlorine. Now, coming back to the relative intensities, R35 chlorine is about 75% abundance, so that intensity is about 75. And then our 37 chlorine, this little peak here, is about 24. So this is almost 25. This one's 3 times that height, which gives us 75. We'll have practice on this in class, but ultimately we're looking at the charge of our substances as well as the mass in order to separate them. And then this tells us information about our masses of the particles and their relative abundance. Cool, so that's 2.4. Hope that helps. Let me know if you have questions over this. Thanks, bye.